Okay, let us go to the topic 3. Static forces on surfaces. Now, we are only looking at the static forces on surfaces when the surface is submerged in a liquid column. Let us consider force system acting on a body. How do we look at for the equilibrium of the body due to the force system? We find the resultant force of the force system. If the resultant force is 0, we call this object satisfy the equilibrium concepts. Now, what are the most important points in a resultant force? We know force is a vector. Therefore, we all need the magnitude of the force. Then, obviously, the direction of the force. We need something else as well. When we look at the equilibrium, we need to know the location where this resultant force acts. When it comes to the hydrostatic pressure force, we call this particular location is the center of pressure. When we limit our studies to fluids, we call this force to be hydrostatic pressure force. We divide this hydrostatic pressure force into two different sections based on the geometry. The first one is the hydrostatic forces on flat surfaces, and the second one obviously is the hydrostatic forces on curved surfaces. Now, let us look at the first case. Hydrostatic forces on flat surfaces. It could be either a vertical flat surface or it could be either an inclined flat surfaces. Now, we know from our basics, the force has to be perpendicular to the flat surface. Now, we'll start our analysis based on the vertical wall submerged in a liquid column. So we are not really looking at the inclined plane at this moment. We are only looking at the vertical wall. Now, we know from our previous study, that is on the hydrostatic pressure, the pressure varies with the height. Therefore, we also can assume that the hydrostatic pressure force varies with the height. Why is that? Because we know pressure is force divided by the area. So if pressure increases with the height, we can have an idea about the force as well. It has to be increased with the height. If that is the case, how can we find the resultant force, since it is a variable? Now let us consider this vertical wall, a rectangular vertical wall. Depth of the liquid column is D and the width is P. Now we are trying to find the hydrostatic pressure force on this particular wall due to the D depth of liquid column. Now the step 1 is draw a constant depth contour at Y depth below the free surface. Now, the second step is give the contour an area of delta A by increasing the thickness of this contour to delta Y. Now, delta A is equal to delta Y, that is the thickness, into B. Now, let us calculate the hydrostatic pressure force delta FH acting on this small area. It is the hydrostatic pressure into the area. At this particular level, we have a hydrostatic pressure of rho gy. So the area is delta A. Now therefore, delta F is equal to rho gy delta A, and delta A is B delta Y. So it is rho gy B delta Y. Now how can we find the total force? It is the integration with respect to the depth. So the force can be found. F is the integral, that is the limited integral from 0 to d rho g by dy. Now if you do the integration, let us assume this is an incompressible liquid, so that you can take rho gb outside the integral symbol and you have y dy. Do the integration, you'll end up with half rho g bd squared. Now that is the hydrostatic pressure force acting on a wall which is d into b in dimensions. Now we found out that the magnitude of the force. How can we find the location of this resultant force? Now when we say the location, we are trying to find the distance from the free surface. It's simple. Let us take the moment. Let us take the moment of our previous section delta A. Now the moment with respect to the free surface is delta m, that is equal to y delta f. So that we can find the total moment by integration from 0 to d. That comes to rho gb integral of 0 to d y squared dy, and ended up with 1/3 of rho g bd cube. Now that is when we consider a small strip and calculate the moment, then calculate the total moment by integrating from the total depth. And also we know the total force. So if that particular force which we found from our previous study, that is the half rho g bd squared acting on a particular location, so that has to be equal to the total moment. So we'll equate the two moments and we'll find out that the location of this particular hydrostatic force is acting at 2/3 of the depth. Now what is the direction? Obviously it has to be perpendicular to the surface. So we found the magnitude, direction, and the point of resultant force acting on this particular vertical wall for the simplest case.